Okay, so today what I want to look at is two projectiles. Let's say they're rocks. Two people are throwing rocks at each other, I guess, that are launched simultaneously at the same speed, but at two different angles. One is launched at some high angle, we'll say is greater than 45 degrees theta, and one will be less than 45 degrees angle phi, such that they actually do land on each other, not necessarily simultaneously, of course, but they will land at each other's launch points, and the launch points are separated by a distance d. And the goal is actually to figure out during this trajectory, remember they're launched simultaneously, during this launch, what is the minimum distance between the two projectiles throughout the entire trajectory? So probably it's not going to be d. I mean, that it could be, I suppose, but most likely as this one gets closer and this one gets closer, somewhere around here, maybe it'll be here. Remember, it might not be halfway because they're not going to reach that halfway point at equal times necessarily. What is that minimal distance, maybe I'll call it r or something like that, between these two rocks as they're flying along their trajectories? Okay, well, this actually isn't too bad. We're going to start by writing down the trajectories of these two equations, or at least their positions as functions of time. We're then going to find this sort of separation distance as a function of time, and then we'll just try to minimize it. Easy. So the first thing we want to do is write down the positions as functions of time. And I'm going to do this in a sort of vector notation style. I'll call the one on the left maybe rock 1. And we know it starts at the origin. We know that it's launched at its initial velocity, which is going to be v naught cosine theta in the I hat direction plus v naught sine theta in the j hat direction. All of that is multiplied by the time t, and it's not accelerating. I'll put a little +0 there. Well, sorry. It's not accelerating in the x direction, but of course it is accelerating in the y direction. So the net term that it accounts for the y acceleration will be a -1/2 gt squared in the y direction only. Okay, so that's the position of rock 1. Rock 2, on the other hand, does start out here. So its initial position is actually going to be d in the I hat direction. And then I'm assuming it's firing to the left. So I'll have a negative v naught cosine of phi times I hat. And then I'll have a plus v naught sine of phi j hat, also times t, and also with the same acceleration term. They're both under the influence of gravity. They are launched at the same time, so these t's really are the same t's. They're launched at the same speed, so these v naughts really are the same speed v naughts. And we're picking up the minus sign there, and the d there is really the only differences. As a little aside, we might want to know if there's any relationship between theta and phi, and there is. In order for these two things to land on each other, the distance between them has to be the range of the other. And we have a formula for the range in terms of the launch angle. Remember that that's going to be v naught squared times the sine of twice the launch angle over g. But of course, that's the same as v naught squared over g times the sine of 2 phi for the other guy. They both go the same total range. And what this tells us is that the sine of 2 theta equals the sine of 2 phi. In other words, theta and phi have to be complementary to each other. And the real way to see this is, well, if the sines are both equal, and of course both of these are acute angles, then the only possibility if theta is not equal to phi directly, and we know that's not the case because I told you one is greater than 45 and one is less than 45, that has to have that, if you expand this out, sine theta cosine theta equals sine phi cosine phi, and if they're not equal, then it must mean sine equals cosine and cosine equals phi, which is the same thing as saying that they're complementary. Okay. What that's going to mean for us here is I can replace all the cosine phis with sine thetas, and I can replace all the sine phis with cosine thetas. So let me write that in here. This will have a sine theta, and this will have a cosine theta. That way I have sort of eliminated one of the angles already just by geometric constraint. Now, what we're actually interested in is not their positions overall, it's their positions relative to each other. So I'm going to define a new vector, I'll call it this R, and it really doesn't matter which one is like number 1 versus number 2. So I'll just subtract them in order. I'll do R1 minus R2. And when we subtract these, some stuff nicely happens. For example, we have a V0 cosine and a minus V0 sine. When I subtract them, I'll end up with a V0 cosine plus sine in the, or times a t in the I hat direction. Okay, that's not so bad. The second piece has something similar happen. Notice that these two acceleration pieces cancel. That's kind of nice. I'm not going to have anything quadratic in time. I will also have, for the other one, what? Another V0 sine theta minus cosine theta t in the j hat. Okay, and don't forget we do still have this one little guy hanging off the end. Now, what I'm actually trying to minimize is not a vector. I don't even know what minimizing a vector means, but I want to minimize the distance between them, which is the magnitude of this vector. Now, it turns out that minimizing the magnitude of a vector is equivalent to minimizing the square of the magnitude of the vector because, well, it's never 0. We know that automatically. So we can just write down that I want to find the derivative of r squared. I don't have to actually take any square roots. It just makes the algebra messier. And the square of this vector, notice I've got both these pieces are the I direction. So it's going to be V0 cos theta plus sine theta t minus d quantity squared plus V0 sine theta minus cosine theta quantity squared. Okay, now we've got to expand this out. Oh, there's a t there too. Let's expand this out. I'll have a V0 squared t squared, I'll pull the t to the front here, times this thing squared. Cosine squared plus sine squared is 1, and then I'll have twice the cross product, or the cross term. That's my first bit. I'll also have a minus 2 V0 dt. Maybe I'll write that as t times d so we're not too confused. It's not a derivative or something. Times this sum. Okay, and then I'll have a plus d squared, of course, for the last term. From this term over here, I'll have a V0 squared, t squared like before, and then when I expand this out, I'll get a sine squared plus a cosine squared, that's a 1, but this time minus 2 sine theta cos theta. Okay, does that simplify? I think it does. For example, this plus 2 something something and this minus 2 something something cancel away. And then I'm left with 2 copies of this, so I have a 2 V0 squared t squared. The middle term, not much we can do about that. And then the last term is a constant. Okay, now for the calculus bit, we want to minimize this distance squared. Notice this is a function of time, so I want to find dr squared dt. The last term goes away, that's a constant. And then I'm just going to pull down a 2 here and get rid of the t there. So this will become a 4. The second term, and the last term is 0. But I want to set this whole thing equal to 0 because I'm trying to minimize this. And I'm going to use that to solve for the time at which these become closest. Pretty easy to do that. It's linear. Notice one of the 2's will cancel. One of the V0's will cancel. Okay, so this is my first answer. It's not really the answer I want. Minimizing means I'm really asking what is the minimum distance, not just when does it occur, but I have an answer to when it occurs. So that's a start. Now I want to plug this back into this expression and do some simplification to rewrite r squared at this, maybe I'll call it t star or something, at this time of minimal distance. So let's bring that to the top. Okay, so here's that expression from previously. Over here I saved our little t star particular value. So now we're ready to find r star squared, which is the, well, square of the minimal distance. Okay, plugging this whole thing in, it'll be a little annoying, but it'll clean up kind of nicely. I'll just go ahead here. There's an extra D and there's an extra copy of that, so won't write that again. Now let's see what this does for us. First of all, the V naught squareds cancel, and the V naughts cancel. These 2's cancel. These 2's don't cancel. I'm going to be left with a D squared in all of these, just for dimensionality. It has to have a D squared. And then this first term will have a 1/2, because one of the 2's cancels. And I'll go ahead and expand this binomial. So, you know what? We've done this before. Cosine squared plus sine squared is 1, and then I'll have twice the cross term. And actually, if you want, you can immediately write this in terms of a double angle formula. The second piece, which is attached to a negative sign, also will expand this out. So I'll have a 1 plus twice the cross term. And then I'll have this little +1 stuck on the very end. Okay. Cleaning everything together, what do we get? This -1 and +1 cancel. I have a 2, well, I have a 1 minus a 2, which is very famously a -1. There's a D squared out front, and then I'll have a 1/2. And when we subtract everything carefully, we'll end up with a -1 sine theta cosine theta. And now to finish the whole thing off, let's go ahead and actually put a 2/2 back in here. 2 sine theta cosine theta is a double angle formula, and we'll go ahead and take our square root. So it'll be D times the square root of 1 minus sine 2 theta all over 2. And I think that's pretty good. There's probably some other trigonometric ways that you can write that in. But this is the minimal distance between the two projectiles at, well, if they happen to swap their launch points. QED.